Hello everyone, this is my lab reports on Lab 1 of 2211. So here's the agenda, what I'll go over in this video. Let's get started with the introduction. So this lab focuses on a moving object at constant velocity after a force is applied. Our job is to compare an observed experimental trial to a predicted computational model that we use data to base off of. In performing this experiment, we're looking to cover two main topics, which is Newton's second law and Newton's first law. Newton's second law can be seen in this velocity update formula, and Newton's first law is states that an object in motion will remain in motion unless acted upon by an external force. So if there's no net force that acts upon the system, neither momentum or velocity will change. Here are some free body diagrams to cover different forces that we'll talk about. So there's normal force, force of gravity, uh, which are present in both. For the initial movement, there's also an applied force, which has acceleration, net force, and an increasing velocity. And while we were tracking it, there was no net force, which means velocity stayed constant. And in our system is the cart, the surroundings, is everything else. So our procedure, we first gathered the necessary stuff for the video. We set up the cart on the rail and gave it a little push. We started recording after we let go of it, and then we imported the video onto Tracker and scaled our values, knowing the lengths that were in the video. After that, we tracked the movement of one point of the cart over fixed time intervals. And then we added the data from Tracker into a spreadsheet. We used the starter code on GlowScript to make changes to the initial conditions to set up for our computational model. Then we took the data from this simulation and added it to the spreadsheet in a different column. At the end, we made graphs for both of them and analyzed. Some of the assumptions we made while running this were that friction was negligible, the table was a level surface, and the ball was at max speed when we began tracking. So we didn't start tracking until after the cart had finished accelerating. The initial position of the cart was 0.202 meters. The initial velocity was negative 1.15 meters per second. This can be seen in our calculations where we just did change in x over change in t. Start time is 0.00 seconds. The mass of the cart is 0.5 kilograms. So the update formulas we used were the velocity update formula, Newton's second law, which says that v final equals v initial plus f net over m times delta t. F net was 0 while we were tracking it, so ended up just being v final equals v initial, so velocity did not change at all. You can see our implementation of the code right here. The position update formula, we took that velocity that we got from velocity update formula, threw it into average velocity, and multiplied it by delta t, and then added it to our initial position to get our current position. And you can see that implementation in the code down here. Um, Computational model iteration. So we used a while loop with while t is less than 1.8 because our max time was 1.8 seconds. Our force vector you can see right here is 0 while we were tracking it. We have our two update formulas here. We also have the time updater as well as the rest of the code, which basically plots our puts our data into like column form and then also shows the model. So here were the results that we got. Here is the results of the model compared to our experimental trial. The graphs look very similar at the beginning, but we can see as time progresses, the experimental model seems to move slower. You can see this with the gentler slope, and this could be caused by non-negligible force acting against the motion, causing it to slow down. So some potential errors or improvements. There were small differences in where the points of the center of the mass was placed for each frame in the tracker, which can impact the position for each point and give false fluctuations in velocity. Also, small rounding errors can make a big difference because a lot of the numbers we're using are small in this experiment. Next time, I think a meter stick in the frame could give us a more accurate result by allowing us to place our tracking better on tracker. So what if all the x coordinates were placed with negative x? All this would do is represent a mirror image across the x-axis, which means that velocity would change due to a change in direction. However, speed would remain the same because the magnitude would stay the same. And then what do these results mean? So because our observed graph was very similar to our predicted graph and almost completely linear, it shows that there are minimal forces acted upon in the system, but there was still some disconnect between the graphs, which means that the net force was not zero. And such forces can include like friction or air resistance or gravity, depending on the tilt of the table. And therefore, it did not follow Newton's first rule because the object was acted upon by an external force. And that's all I got. Thank you.